Hello, fellow scientists. Welcome back for the third lesson regarding nuclear transformations. In this lesson, we will take a look at fission and fusion. So first, I want to talk about a historical event. So during the Second World War, the Americans bombed Japan as retaliation because the Japanese had attacked Pearl Harbor. The Americans used the atomic bomb on those two cities. So as you can see here, it's very powerful, it's very energetic, and sadly it killed a lot of people. So I'm putting this in context because we are going to talk about now nuclear fission. So that was an example of what nuclear fission can unfortunately accomplish when it's used in a negative way. So what is nuclear fission? When the nucleus of a very large atom, something that is very unstable, splits in two or more smaller or lighter atoms, so with smaller and lighter nuclei, this can cause nuclear fission. Now, you will notice here that I put the S's in red. So there are two S's, and that's a way for me to remember that nuclear fission, the end result, the products, on the product side, we will find at least two different substances. So nuclear fission produces two or more substances. Okay, so as I said before, when you have an uncontrolled nuclear fission reaction, you can have an explosion like in Hiroshima in 1945. So as you saw, it can be very powerful. Now, how does this happen? So essentially what you have is a neutron that collides with a radioactive atom. So in this case, we have uranium-235. And so the shock essentially of the neutron colliding with the nucleus of uranium, that splits it into two smaller atoms, in this case, cesium and rubidium. In the process, more neutrons are expelled from the original nucleus, and those neutrons are going to basically become this neutron here. They're going to go and collide with other atoms, and it becomes a chain reaction. Now, this collision creates a certain amount of energy. So if all of these atoms, a little bit like a domino effect, if all of these atoms react one after the other, or many of them are reacting at the same time, this produces a tremendous amount of energy. Now, if we write this in a reaction equation in that form, this is what we would have. So we have uranium that collides with a neutron, or a neutron that collides with uranium. Uranium splits into two atoms. So you had one example before. It could split in various atoms, different size. So another example would be Kr and Ba. And as I explained, there's two neutrons that get expelled by this reaction from the original nucleus. Okay, now, as it says here, the atomic numbers and atomic masses must be equal on both sides to respect the law of conservation of matter. So a little bit like we did in the previous lesson, we are going to take a look at the masses and the atomic numbers to make sure that everything balances out, and it should. So 235 plus 1, that gives us 236. 95 plus 139 plus 2 times 1 gives us 236. So the masses are equal on both sides. The neutrons should also, the protons should also be equal. So we have 92 for uranium, and on the other side we have 36 plus 56. That gives us also 92. So the law of conservation of matter is followed. It is respected. Okay, so that's an example of an equation for fission. There's always one neutron that collides with our original substance on the reactant side. Our original substance breaks up into two smaller atoms. So that's why my two S's were red, to show that there's at least two products, and there are two neutrons that are kicked out of during the whole process as well. And those neutrons will go and collide with other atoms of uranium and continue the process. So that's for fission. Now, nuclear fusion is a little bit different. So in this case, it's kind of the reverse in a sense. You can see that I only have one S, in this word, and it's colored in red. So in other words, we are making one product. So what happens is you have two small atoms, and they join together. They collide and they join together. They fuse, literally, and they form a heavier nucleus, so a bigger atom. The hydrogen bomb is an example of a reaction involving fusion. The sun also creates its energy through the reaction of fusion. So the energy that we get, that heat, that warmth that we get, and the visible light and the UV rays and whatnot, they all come from nuclear fusion. Now, how does it look like in terms of a reaction? This is what happens. This is one example. So there are three isotopes of hydrogen. There are two of them that are heavier than the one we're used to. So we have deuterium, dew as in deuce as in two. So this atom of hydrogen has two particles inside the nucleus, one neutron, one proton. And we have here tritium, so tri, three. So three particles inside the nucleus. So we have an atom of tritium and an atom of deuterium that collide together. Now, if all five particles were to combine into one nucleus, it would be a little bit too unstable. That's too many particles for an atom of hydrogen. So what happens is only four remain, so two protons, two neutrons, and at that point, if an atom has two protons inside the nucleus, automatically it has become helium, because we know that the number of protons determine the nature of the element. Now we're missing one particle, one neutron. What happened to it? Well, it's loose. So it's kicked out of the whole process. So it's just flying around on its own. And the whole process, again, releases a lot of energy. Now, how do we write this in a reaction equation? So it can look like this. Okay, so we have deuterium, so mass of 2, 1 proton. Tritium, 3 particles, 1 proton. That turns, after colliding, into an atom of helium and 1 neutron, and of course some energy. If we look at the math of it, 2 protons, 2 protons, 2 plus 3, 5 for the mass, 4 plus 1, 5 for the mass. So the law of conservation of matter is followed and respected. This works. So that's an example of an equation for fusion. So this is not the only one, but it always revolves around the fact that you have two small atoms that combine to make one bigger atom. And that's it for fusion and fission. And that's the end of nuclear transformations. So if you have questions, you know what to do. Post them in the comment section below. And otherwise, I'll see you around for your next lesson. And until then, take care.